Audio. Start video. Brendan is with us already. Good deal, Brendan. Now, does that show up? Yeah, not too bad. Not too bad. Brendan's with us. Let's see who else we got here. Brendan, it's just you and me. Unmute and say hi. Brendan's getting his coffee or whatever. Hey, we got Ben. We got Ben also. Good deal.
Hello, Mr. Griffin. Sorry, I had my mic on mute. I was sitting here talking to you the whole time.
How about that? You're just talking to outer space.
That's
Brendan.
the usual, right?
But we should get used to it by now. Nobody listens to us. Brendan and Ben, you have, we got 6 minutes before class. You have any questions for me?
I think I'm pretty good. I already did the test. It was pretty simple.
Good. Excellent.
Pretty straightforward, but yeah.
Well, I'm going to start grading those. I think officially they're due tonight, aren't they? Here, let me write down.
I think it's tomorrow night.
Is it tomorrow night?
Yeah, it's September 18th at 11:59.
Here, let me write that down officially here. It says here, your exam is the 18th at midnight. Okay. Well, that's tomorrow night. And the exam is due Friday. Today's Thursday. Now there's also homework. I'm such a nice instructor. I don't leave you without any homework. That's good for you. And I think it's problem 230. Problem, and this is homework number 9. Homework number 9. Yeah, I believe it's 230, and it's due. Well, I think it's due tomorrow night also, same time. Yeah. So you need to get started on that too. Okay, great. So you got something to do there. And then the next meeting is the 10th. Is that right? It can't be right. No, that's not right. I think yeah, here we go. The next meeting is the 17th. Right? What's today? I'm getting all mixed up. Today's the 17th. The next meeting is not till the 22nd. Okay. Well, wait a minute. This says problem set number 10 is homework. We'll get this straight in a minute. Homework number 10, that's problem 3.5. I think it says 3.5. It's on page 102. And it's not due till the 20th. Well, when's the 20th? Sunday? I think it's due Sunday night. So you got some stuff to do there. If that's not right, please inform me now. I think that's right. Okay. We have 2 minutes before class. Here's your chance to speak up and ask or comment. Go ahead. Let's see what we got here. We have, oh, we got a good crowd. Ben Harris, Ben Seaman, Brendan, Ashley, Braxton, Samuel, Nicholas, Muhammad, Darren. Good crowd. Okay, guys, any last words before we officially begin now? All right. Well, let's officially begin then. We're studying properties of materials. It's chapter 3. Let me find it here in the book. Chapter 3. Okay. Now the big deal in chapter 3 is this stress-strain diagram. Stress-strain diagram. It's a diagram like this. Normal stress, normal strain. And you need to know, these diagrams are kind of like fingerprints. Did you know each one of us has different fingerprints? No two people have the same fingerprints. Did you know even identical twins have different fingerprints? They have the same DNA, but they have different fingerprints. And when you come talking about different alloys of steel, I don't know how many different alloys of steel there are, just maybe hundreds. But if you talk about all the different metals, you can put in nickel, carbon. You can talk about aluminum alloys. There's thousands. They have a fingerprint, kind of like, only it's a stress-strain diagram. And it's unique. If you take a particular alloy of steel, for instance, see they have some sample ones in the back. They have A6 structural steel. They have stainless steel. They have tool steel. They have other stuff back there. Brass, aluminum. They have a stress-strain diagram that's as unique to them as your fingerprints are to you. They identify the material. Now you need to know a few terms here when it comes to properties of materials. There's brittle and ductile materials. You guys can read all that. All of that is in the. It's on the blackboard. You can read it. It's all right there. But when it comes to materials, there's a brittle materials and there's ductile materials. And the difference is brittle materials don't have a yield region. Like for instance, concrete goes like this, pow, with no warning whatsoever. They have a concrete tester. They go out to the highway and they take a core sample of your road, concrete, asphalt, whatever it is, and they bring it back to their testing lab, and they put it under a lot of pressure, and they increase the pressure, and they increase the pressure, and they increase the pressure, and all of a sudden, without warning, pow! And sand, there's sand in that concrete. It goes flying all over the place. You want to have your safety glasses on when they do that test. There's no yielding. It's brittle. Whereas steel has an elastic region that comes up here. It's really very, very steep. It's very steep, and then it flattens out. And then it does all kinds of crazy things. And then finally, kapow, it will break as you increase the tension on your steel. It will break. But this right here is called the yielding. Well, all of this is called yielding. But see, steel has yielding brittle materials done. This place right here is called the yield strength. The symbol is sigma Y. It's called the yield strength normal stress. That's the name of it. It's the yield strength normal stress, and they have tables of it in the back. You go back here in the back, and oh look, there's the yield strength of different alloys of aluminum and copper and brass and steel. They're all in the back. It's called the yield strength. Now, to be honest with you, some of these materials don't go exactly flat like that. Let me show you what they'll do. Some of them will come up here. They'll have a straight line, all right. It's a straight line. It's a straight line. But then it kind of curves a little bit like that. And pow, like that. So where exactly do you put the yield strength? Do you put it here? Do you put it maybe, I don't know, in here someplace, or where it starts to turn? Where do you put the yield strength? Well, they made an agreement. They come over here at 0.002 nothings. Remember, strain is dimensionless. And if you come up here parallel with the same slope, remember the slope is called the modulus of elasticity. It's the slope of the elastic region. See, this is the elastic region. Everything else is the plastic region. That's not exactly parallel. Let me try again. Parallel is more like, maybe like that. If you come up here parallel and you hit this, and then you go over, that is defined as the yield strength normal stress for 0.2% permanent strain. It's got a fancy name. Can you read my writing? That's supposed to say plastic. That place right there is called the yield strength for 0.2% permanent strain. Remember, this here's strain. We got strain down here. And see, 0.2% is equal to 0.002. You guys all took grammar school percentage math, you know that. And so if you go parallel to your same slope here, and then go over, they call that your yield strength for 0.2% permanent strain. See, this right here is your permanent strain. What you got to understand is when you take the load off, see, you're increasing the load, you're increasing the load, you're increasing the load. Right here, if you take the load off, if you quit stretching it, you've got this sample, this specimen, and if you take the load off, it recovers elastically. And this right here, if you go straight down, that right there, let me color that green. See that green right there? That's your strain recovery. That's the name of that. That's called your strain recovery. And this right here, why don't I color that maybe something? That right there, that's your permanent strain. Permanent strain. Permanent strain. Did that show up? Yeah, I think so. Well, there's brittle materials, there's ductile materials. Ductile materials have a yield strength, brittle materials don't. Any questions so far? Okay, well let's talk about hardness and softness. I'm going to erase all this. I need the room here. We talked about brittle materials and ductile materials. You could read the book. You don't need me. You could read the book. But there's something else called hardness and softness. Hardness and softness. Hope you can read my writing. Okay, there's a diagram in your book that explains this really good. If you look on page 90, they have a stress strain curve for a bunch of different steels. What's interesting is they all have the same slope. They all have the same slope. But see, spring steel has a yield strength way up here. And hard steel is right here. This is hard steel. This is on page 90. This is spring steel, what they make springs out of. This is machine steel. It's pretty dang hard. And then this is structural steel. It's right in here. You guys could read this. These are all different kinds of steel. And then there's soft steel. There you go, soft steel. See, these are the hard ones. These are the hard ones, and these are the soft ones. And it's the yield strength. See, the hard ones have a big yield strength, and the soft ones have a small yield strength. That's the difference between hard and soft. If it's steel, if it's the same molecular structure steel, the same alloy, then it has the same slope. It has the same modulus of elasticity. Remember, Hooke's law goes like this. And it's kind of like an equation y equals kx. You guys studied algebra. That's the slope. If you plot up y equals kx, that's the slope. Well, if you plot up sigma equals E epsilon, That's the slope. Now, how do you make a steel hard? How do you make it soft? There are three ways to make a metal like steel hard. I will ask you guys. I don't want you to fall asleep. Samuel, unmute. Samuel, say hello.
Oh,
Hey, Samuel, I'm just going to ask you, do you happen to know the three ways of making steel harder?
no.
That's okay. You're going to learn. I'm going to tell you.
Okay.
One way is the impurities they put in there. High carbon steel is harder than low carbon steel, so they can put other things in there like nickel, for instance. But the alloy changes the hardness. That makes sense. That's one way. Now, another way is if you ever watched the old blacksmith there on, well, what's that show they had? Can't think of the name of it, but they had a blacksmith on there, and he would get a horseshoe that was red hot, and he would stick it in a barrel of water. Of course, it would steam and cool down. That makes the horseshoe hard. That's another way of hardening. Now, another way is by stretching it, putting a lot of tension force on it, and then, like for instance, if you'll take your steel and come up here, put a lot of stress on it, and then back off. Well, then you know that it will recover elastically, and you have now a graph, a stress strain graph that comes way up here and has a very big yield strength. They call that strain hardening. It's called strain hardening. They just they kind of overload it and then take the load off, and what they've got left is a hardened steel. Okay, well, there's the three ways that they harden steel. Now we've talked about hardness and softness, and ductile, and what was the other one? There's ductile, and there's the other kind. What's the other kind? There's ductile, and there's something else. Let me ask somebody. Nicholas, there's hardness and softness, and there's ductile and something else. What's the other one, Nicholas?
Brittle.
I'm sorry?
Brittle.
Yeah, brittle, that's right. They're ductile and brittle. Yeah, okay. Yeah, we talked about that. Ductile and brittle. When I think of brittle, I think of peanut brittle. I don't know if you've ever eaten peanut brittle, but it's pretty good stuff. They have Spanish peanuts in there. It's kind of a brown color, and it's real hard, and it snaps. It's brittle. It's not ductile. Now, if you want something that's ductile, take a piece of chewing gum. Take some Wrigley's Spearmint chewing gum, and take that chewing gum and bend it. Well, it doesn't snap. It doesn't break in two. It just bends, doesn't it? See, the chewing gum is ductile. Peanut brittle is brittle. That makes sense. Okay, now there's also there's also stiff and spongy. Let me show you the difference there. What we're talking about are different materials and their properties when you make a stress strain graph. See now, a stiff material has a very big slope. There you got a big slope, and it goes on there. See, that's stiff. And here's the spongy one. Spongy material, there you go. Look, the slope is smaller. Spongy materials have a small slope, and the name of that is the modulus of elasticity. And you can go in the back and look it up. Like, go back here, modulus of elasticity. Well, there they are. They have some numbers that are big and some numbers that are small. Like, for instance, they have an aluminum one. It's 10.6. And, well, what it says is 10 to the third KSI. That, if you look in the back, you'll see this for one of those alloys of aluminum. Now, I would write that as 10.6 MSI. Because if you have 10 to the third KSI, that's equal to an MSI, all right? But down here they have structural steel. They have the modulus of elasticity for structural steel is 29. Then they have that 10 to the third thing, KSI, but I would write that as 29 MSI. Well, you know what? This one here is the spongy one. Because see, the slope is smaller. See, that slope is small, and this slope is big. This is the stiff one. And this one's the spongy one. And you can look them up in the back. Do we have any questions so far? Okay, well, let's talk about how much energy that you can apply to your specimen of whatever alloy it is before something bad happens. They have two measures of how much energy that a particular material can withstand. They have the modulus of rigidity. I just had a senior moment there. You guys could read all this in the book. It's the modulus of resilience. I said it wrong. The little symbol is U with an R under it. This is in your book. It's on page 95. It's called the modulus. We'll do a little bit more theory and then we'll work on some problems. I know you love the problems, but they're based on the theory, so we have to suffer through a little theory. Now, this is called the modulus of resilience. And they also have a thing called the modulus it's got a little T underneath it. This one's on page 95, and this one is on page 96. And this is called the modulus of toughness. Modulus of toughness. Now, what this modulus of resilience is, in the elastic region. Now, somewhere up here, you reach the end of the elastic region, and then stuff starts to happen. You enter the plastic region, and all kinds of stuff happens here. But this modulus of resilience is the area, it's the area underneath your elastic region. See, this is your stress strain curve. And you guys all know how to measure a triangle. You go 1/2 the base. Now this has a name right here. It's called, oh gee. Why don't we just call it the, never mind, I'm not going to call it anything. I don't want to tell you the wrong stuff. What this is going to be is 1/2 the base times the height. See it there? Here, let me do it this way. They have a material called, these are fictitious. They don't really have materials like this, but they have a material called a elastic perfectly plastic materials. Let me write that for you. Elastic, it's just a model. It doesn't exist in the real world. Elastic perfectly plastic material. If you have one of these, which they don't exist, but we're just pretending, then you have this perfectly elastic region, comes up to here, and then it goes plastic, and then the plastic is just absolutely flat. Isn't that nice? That's not what the real materials do. But in this case, this would be your yield strength. And this would be your yield strength normal strain. And so you could put your yield strength normal strain and your yield strength normal stress right there. And you would have 1/2 the base times the height. You would have this area. Okay. Now let's look at the units. The units are nothings for strain. And usually these are in what? Megapascals? Yeah. Well, I think we were doing English, senor. And they were MSI, weren't they? These were in MSI that we were looking at in the back. And of course, the 1/2, that doesn't have any dimensions. And so this has dimensions of MSI, but that's not what we want. What we're going to do is we're going to try to write it in terms of energy per volume. That's what this is. It's energy per volume. It's energy per volume. Okay. How are we going to do that? Well, see what this is. You know what that is? That's well, it's mega. Never mind the mega, but it's pounds per square inch. It's pounds per square inch, basically. It's a megapound per square inch. Well, we can get that in energy. We can get that in energy per volume by simply multiplying by inches over inches. And did you know a pound inch is a unit of energy? a foot pound is a unit of energy, and an inch pound or pound inch is a unit of energy. And so what we have is inch pounds or pound inches per cubic inch. We have the energy per volume. What does that mean? That means you can absorb this amount of energy per volume, and then if you'll remove the stress, your piece will return to its original shape, and you'll never be able to tell the difference. It's kind of like with a rubber band. Take a rubber band and you can stretch it, and then remove the stress, and it'll go right back to where it started with no permanent deformation. That's what the modulus of resilience is. It's the energy per volume. Now, usually though, they put this in foot-pounds per cubic feet. Now, here's how you could do that. You know that there's a square foot for every, wait a minute. I'll get this right in a minute. How about this? Let's go, a foot is, I'll get this in a minute, just a minute now. How about this here? 12 foot, uh, 12 inches is a foot. We all agree with that. You're not going to argue with me on that. Now, if you cube this, if you cube it, I don't want to cube it. That'll get rid of the cubic inches. No, I just want to square it, I think. Now let's see what we got. We got rid of all the inches, and we have, what I want is foot-pounds per cubic foot, is what I want. What if you cubed it? Then what you'll have now is you'll have 12 cubed inches per cubic foot, right? Did I do that right? You'll have 12. You'll have 12. Guys, I got confused. We'll do it on a problem, and it'll make sense. But right now, the main thing is, you know that the modulus of resilience is the amount of energy you can absorb, and when you take it off, you'll go back to the way you were before. And we'll get it in a minute. Now this here is called the modulus of toughness. Now what that is on a real alloy, you know, it doesn't come up here and go straight, because these materials are not perfect. They do all kinds of weird things. They come up here and then kapow, they will fracture. And what the modulus of toughness is, it's not just the area under the elastic region, it's the whole dang area under the whole dang graph. That's the modulus of toughness. And what it amounts to is the energy per volume that you can absorb before fracture, all the way up to fracture. It's the energy that your substance can absorb all the way up to fracture. And on page 96, they have three different steels. They have a hard steel. Now remember, the hard steel comes up here. It goes way up here, but then kapow, it fractures here. And so the modulus of toughness for it would be that area under it. And then they have structural steel. That's more like this one. And it has a very large area under it. It can absorb a tremendous amount of energy per volume before it fractures. And then they have soft steel. Soft steel is down here like this, and it fractures. And the amount of energy it can absorb is this area under it. Well, it turns out that the area underneath the structural steel is bigger than the area under soft steel, and it's bigger than the area under the hard steel. And so that's why they use rebar that's made out of structural steel. It can absorb, car runs into a bridge, okay? And the bridge breaks, but it can absorb the most energy. That structural steel can absorb the most energy all the way up to fracture than any of the other alloys. And we'll need to work a problem on that. And I'll try not to get confused. Well, that's all the wonderful theory for right now. We're going to work some problems now. But do you have any questions? I wonder if anybody's still awake out there. I'm hoping. Okay. All right, let's work a problem. You guys should read all your book there on that. But this one that I wanted to do with you is, it's F311. Fundamental problem 311. Now let me find it. Help me find fundamental problem 311. Aha, I found it. It's on page 101. And we could even do the modulus of resilience and modulus of toughness on that. That would be fun. Okay. All right, let me read this. Let's see, it's, well, they've got this graph here. Let me draw this. Got a stress strain graph. Remember, these are like our fingerprints. And this goes up to here, and then it goes over to here. This value is 450. Does that show up? Yeah, that shows up. And this value right here, that's 550. And these are megapascal. Megapascal. Okay. And now this value right here is 0.00225. 225, nothings. Strain doesn't have units. And this value right here, come down to here, is 0.03. 0.03, okay, great. So what? Well, first of all, I want you guys to find the modulus of elasticity. Find the slope. I'm going to shut up for a tiny minute. See that this is the elastic region here. This is plastic region. And I'll be quiet. Find the slope. Go ahead. I'm going to do it, and then I'll call on one of you guys. Find it. Okay, well, let me go to one of my excellent students here. Well, why don't we go to Alex? Alex, unmute and say hi.
Hello.
Hello. Alex, do you have this modulus of elasticity for this elastic region here?
I got 450.
That's
It was
not
just the
what,
0.00225 squared, and then the 450 squared, right?
no, it's just rise over run, Alex. See, this,
I overcomplicated it.
and boy, you sure did. See, it's a slope. Now, Alex, I know they taught you in school
That's
that
a much bigger
slope is
slope.
rise over run. So the rise is 450.
Is it 200,000?
It's you got the number right, but the exponent is not right. Do it again.
The exponent's not right.
Well,
Oh. Is
see
it because
that's
of the megapascals?
Alex. That's a million. See that M?
Yeah.
That's a million. Do it again, Alex. What do you get?
I get 2 to the 14th power.
You're getting closer, but that's still not right. Did you divide by the run, which is 0.00225?
Yeah, okay, let me redo it one more time. I'm getting 2 times 10 to the 11.
That's correct. Good going, Alex.
Hey.
Good going. All right. Now, they usually write it like this, Alex. They'll go, and it's here. What Alex got is right. They got 2 times 10 to the 11th. And those units are pascals. 2 times 10 to the 11th pascals. But they usually write it like this. 200 gigapascal. See, if you make this, multiply that by 100 and divide that by 100. See, if you make this one smaller, you got to make this one bigger, and you get 200 times 10 to the 9th. Well, that's a giga. So we just figured out our slope. It might be fun to go in the back and see if we have any that are in that ballpark. Can you find any that have a 200 gigapascal modulus of elasticity? I'm still picking on Alex. Alex, go to the very back page of your book and look for a 200 gigapascal and tell me what you find.
Okay, where is this in the back of the book?
A very, very back flap page in your book.
Okay, I'm using an online text, which is why I'm asking.
Okay, take your time. Can you do they let you look at the back page on that online text?
Like the very, very back page?
Yeah, the very, 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 very back.
Yeah, it just says useful references, fundamentals, equations of mechanics. Is that what we're looking for?
Maybe. We got to know how to, all of you, see, I'm picking on Alex, but this is for all of you. You've got to be able to find these tables in the very back. And Alex is trying to find his now.
Yeah, I'm not finding it.
Somebody out there, we got a whole crowd of wonderful students. Somebody out there, can you find it? Can you find a 200 gigapascal modulus of elasticity for the property?
Nickel steel, maybe?
Now let me look and see. Nickel steel. I don't see a nickel steel back here. Where do you see?
Sorry, I'm not looking at the book. There, I use a engineering toolbox site for
Well,
it.
that's okay. What you said is probably correct. But I want to teach everybody to be able to get to this table in the back of their book. Now, who was I just talking to?
Darren.
Darren, thank you for contributing that, Darren. But I need somebody back there. We got to be able to find this table, or we're in trouble if we can't find this table. Somebody out there, tell us how you get to that table with your online book.
Is it the steel alloys?
Say that again.
Is it the steel alloys?
Yeah, it is. Which one is it?
A36 and A992, they both have.
Yes,
modern-
that's right. And you found, that's Mohammed, isn't it?
Yes.
Mohammed, you found that table in the back of your book or your e-book, didn't you?
No, I have the physical book. I don't
Oh,
have.
you
an
have a
ebook.
physical book. Okay. It's probably structural steel. It's probably A36 structural steel. Now, I need to talk to somebody that can find that table in their book. Can anybody do that? Kind of worried about you guys. How are we going to be able to look up stuff if we can't find this table? The name of the table is Average Mechanical Properties of Typical Engineering Materials. Well, I don't want to take up all hour for people trying to find something. We have to go on, but we found the slope. It's 200 gigapascals. And if you can find the table, that's most likely structural steel. Okay, well, let's go on. And if anybody can find that table on your ebook, please unmute and tell us, okay? But right now we're doing F311, and let's see where we are here. 311, I got lost. Here we go. Now they had a specimen that was 50 millimeters long. Well, here, let me draw it. I'm going to draw it here. It's 50 millimeters long. And they said there's 150 kilonewtons tension on it. $150 kilonewtons tension on it. And they said the diameter is 20 millimeters. 20 millimeters diameter. So see, we can get the stress. The stress is just the force, 150 kilonewtons, divided by your area. So I want you to do that for me, and I'll call on somebody. Find the stress. I will shut up for 1 minute. Find the stress on that specimen.
Mr. Griffin? Mr. Griffin?
Yes.
The diameter is 0.0020, not 50.
This is this is wrong. Mohammed, you just got a nice thank you point. The diameter is 0.02. I don't know where I got the 05 from. Okay, go ahead and get the stress now. Now that Mohammed has helped us by giving us the correct diameter. Okay, let me pick on Mohammed. Mohammed, what'd you get for the stress?
Just a minute. I got 477,464.28.
Yeah, now that's correct, Mohammed, but we need to know what we really need is megapascal. Can you write that in megapascals for me? He's got the right numbers. See, we want the stress in megapascal. So what do you think it is in megapascals, Mohammed? What, Mohammed, just tell me what you got. What was the number you quoted? Let me write it down. What did you say it was?
It's 477,464.
477,464.
0.82.
0.82. Now I need to know what the units are for that, Mohammed. What goes in these units here?
It's gonna be kilopascal.
That's right, kilopascal. Good going, Mohammed. But now we want megapascals. So what we're going to do is we're just going to write this as 477. Why don't I just round it off? And now we have megapascal. Mohammed, do you understand that?
Yeah, I got that too.
Good, excellent. Okay, now let me show you where that is. It's darn close to halfway between here. See, 475 would be exactly halfway between, wouldn't it? Would it? I don't know. Would it? 475? No, wait a minute. No. It wouldn't either. See, there's 100 difference there, huh? And we're only going 27. You know what? It's about here. It's about in here. The 477.5 megapascal. It's about a quarter of the way, isn't it? Because see, halfway, in fact, it's a little smaller than I have it there. It's more like that. About in there. Because see, halfway would be 500. Halfway between 450 and 550 is 500. We got 477.5. We're right about there. I need to know what this strain is right here. If you come straight down, I need to know what that strain is. Okay, well, let's get that. We have a little triangle right here. Here, let me put it in green, okay? You see this little triangle in green right here? And then we have a big triangle in green right here. Those are what they call similar triangles. Hopefully you guys took geometry in school. And so you can set up a ratio. You can say this little distance here, which I think is, well, it's 27.5. See, if you go from 450 to 477.5, I think that's 27.5 is to this little distance here. Here, I'll make these black. There you go. And now this little distance here, we'll just call it epsilon for right now. In the little triangle, we'll equal this big distance here, which happens to be 100, I believe. To go from 450 to 550, that's 100, right? Now, wait a minute. No, wait, no, I'm doing this wrong. That's 500. I wrote that wrong. I need you guys, I need somebody out there to help me here. That was wrong. And then we're going to get this right, though. But it wasn't 550, it was 500. I wrote down the wrong number. Okay, now what I'm going to do is, it turns out that the 477 is dang close to halfway between. That puts us right about here. See, the 477.5 megapascals is pretty close to halfway between 450 and 500, isn't it? Yeah, because see, the difference is of 50, and you've got a 27.5 difference. Now, what I really need now, what I really need is, I need to know what the strain is here on our piece. See, this piece is going to be longer, and we can find out how long it is. And here's the plan. I'm going to make two triangles. There's one here, and then there's a bigger one here. Yeah, there we go. And I'm just going to set up a ratio when you have, what do they call those? Similar triangles. Here, let me write this value for E here. E is 200 gigapascal. All right, now I'm setting up a ratio. This little distance here is 27.5, and this distance here is, I don't know what it is. We'll just call it delta epsilon for right now, from here to here. Delta epsilon. And that should equal this distance here, which is 50. See, from 450 to 500 is 50, right? I think so. Yeah. Now these happen to be megapascals. But see, that's going to cancel out. So we don't really care that they're megapascals. And here we're going to take this distance here, which is 0.03 minus the 0.00225. See, that'll be that distance from here to here. And we can solve for this little distance delta epsilon right here. And then once we have that, we can add it to this and find out what our strain is. And we can find out how long this thing is. Do you understand? It's going to be longer. And we're going to find out how long it is. Here goes. Put this in your calculator with me and find out how big this little delta epsilon is that I have right here. Again, I will shut up. Can you do that for me, please? Well, I got a value. of 0.01526, I don't know, blah, blah, blah. Now remember, that's nothings because strain doesn't have any units. But if you want this value of strain right here, you're going to have to add the 0.00225 to it. Okay, let's do that. We're going to add 0.00225. There goes. I'm going to add that now. And here's what I'm getting, 0.0175, 0.0175113. There we go. We now have our strain. Now I can figure out how long this thing is. Here, let me draw you a picture. Now, before you put this 150 kilonewtons on it, it was 50 millimeters long. But see, we're going to put the 150 millimeters on it, and it's going to make it longer. Here, I'll exaggerate it. You wouldn't even be able to tell, but see, I made it longer. And we're going to figure out how long it is. Well, I'll tell you what it's going to be. It's going to be 50 millimeters times, we found out what this strain is. It's 0.017513. So if you go 1.0175113 times 50, that'll tell you how long it is. See, it gets longer by this amount of strain. So you have your original length, 1 times 50, plus the strain times 50. Now let me see what that is. It made it longer. It's going to be, I'm getting, this thing is not 50 anymore. It's 50.8756 millimeters. Hey, it got longer, didn't it? It's stretched. Now, if you read the problem, if you just tuned in, we're doing fundamental problem 311, and see there's answers in the back. We can go back and see if we did this right here in a little bit. It says here, the 150 kilonewtons is applied and then released. And they want to know the permanent elongation of this specimen. Well, see, we haven't released it yet. Here's our piece. And this is how long it is with this, what would they say it was 150 kilonewtons. Let's put that on.
Mr. Griffin?
Yes.
I think you put the wrong value for the E.
Mohammed, a little louder, please.
I think you put the wrong value for the E on when you multiply with the 50 millimeter. It was 0.0175. I think we have 1.01753 when you multiply with the 50 millimeter.
Okay, now when you solve here, you get a different answer?
No. I'm saying when you multiply with the 50 millimeter for the new length,
Yeah.
you multiply with 1.0175.
Oh.
It's 0.0175. Because I'm getting 0.8756 millimeter.
Okay, now just, Mohammed, thank you so much for speaking up. I appreciate you so much, but I didn't quite understand. Are you saying that this is wrong? What do I need to multiply by?
Okay, so look at the figure where you multiply 50 millimeter with 1.017513. Did you see that?
Yeah, 1.0175. Yeah.
But on the bottom, we get 0.017513, not
0.0175. Yeah. Okay. So what you want to do is you want to take 50 times 0.017513. Is that what you want to do, Mohammed?
Yeah, yeah.
Okay, now what that will give you, Mohammed, is the amount that this stretches, see? That will give you the amount of elongation that it stretches. But if you want the total length of it, that's not the total length. You have to add the 50 to it, right?
Yeah.
So let me do that. Let's see. That's 50 times 0.017513. I'm getting 0.8756.
Yes, that's what I get.
Yeah. Now, to get the total length, that's just how much it expands, Mohammed. You have to add, if you want the total length, it was 50. Now, this little distance here is 0.8756, right? And so the total is 50.8756, right?
Oh, okay, I got it now.
Okay. Now, Mohammed doesn't get another thank you point for that, but I still appreciate it. But you're okay, aren't you?
Yeah, I'm okay now.
He's okay. Good. Excellent. Okay, now here's what we're going to do now. We're going to release that. We're going to take that force off. Now, when you take that force off, here's what happens. It recovers elastically. It comes down here. I'm glad Mohammed spoke up, because some of the others might not understand. See, this is called the recovery. I'm trying to draw this parallel. It has the same slope. When you take the load off, it recovers elastically. Do you understand? And so now, what I want to know now is, where the heck are we here? Well, we can find it because we know what the slope is. We have a nice triangle here, and we know the slope. Let me make a little room here. See, here's what I'm telling you. Now, I hope you're taking notes because I need the room here. What we're going to do is we're going to take this 150 off. And what we're going to wind up with we're going to wind up with a specimen it'll be longer than it was originally because it's going to have permanent strain. Does this come out? Yeah, this is called permanent. It's called the permanent strain. It never goes, that thing's never going to go back to the way it was. It's permanently stretched, even when you take all the load off. And notice it's going to be a little bit longer. See, it was this long. And then you put the load on it and it became longer. And we now know the new length. And then when you take the load off, it will shrink back some, but not back to the original. It shrinks back elastically. And we're going to find that. Okay, now to find that, we have a triangle here. Here, I'll draw it for you. It's got there's a triangle here. You see it? There's that triangle. And now we know the slope of the triangle. The slope is 200 gigapascals. We figured that out earlier. I forget which excellent student helped us on that. And we know what slope is. It's rise over run. Well, the rise from here to here, we know what that is. It's 477.5 megapascals. That's the rise. And the run, see this run here? They have a name for that. It's called the, well, I'll make a symbol. I'll call it delta epsilon. I hope you can read my writing. delta. They have a name for it. It's called the strain recovery. See this distance right here is called the strain recovery. And see, I don't know what it is, but look, we have an equation with only one unknown. We can find the strain recovery, can't we? Okay, now I'm going to shut up for 1 minute. I want you to find the strain recovery. We got the equation. It's just rise over run. Plug it in. Get the strain recovery for me.
I know. I'm trying to put.
Okay, how about my friend Ben Harris? Ben, unmute and say hi.
Hello.
Hello. Ben, do you have this strain recovery from this equation for us?
Let's see. Is it 2 times 10 to the negative 9?
Nope. Giga means 10 to the 9th. Did you have 10 to the 9th for that giga?
Yeah, I did 477.5 divided by 200 times 10 to the 9th.
Yeah, now don't forget that M stands for 10 to the 6th, Ben. So do it again with a 10 to the 6th, that's a mega.
Okay, so 0.002385.
By Jove, you've got it. This is the strain recovery. It's equal to 0.002385. Ben, I'll pick on you one last time here. What's the units? What's the units for strain?
Oh, for strain, there's no unit.
He's got it. He's catching on. There are no units for strain. But now we have this strain recovery, and now we can get the strain right here. Yeah, we can get the strain right here. Because see, I know what the strain is here. It's 0.017513. And if I just subtract this strain recovery, I can get the permanent strain, if that makes sense. So let me do that. We're going to take the strain. We worked hard to get that strain. That was the strain here when the piece was under stress. It's 0.017513. And see, we're going to subtract the strain recovery, which Ben has is 0.002385. See, this is the recovery, and this is the strain we have under the load, with the load, the strain under the load, and then if you subtract those, we'll have our permanent. We're going to have our permanent strain. All right, I'm going to do that now. All right, I subtracted those. And here's what I'm getting. I'm getting 0.00 0.0151, I don't know, 25. You can get kind of carried away with all these numbers. We think we have the permanent strain now. It's 0.015 something. Now we can find the final length after you release the load. You can find this final length. I tell you what it'll be. It'll be 50 millimeters times the strain, which is 0.015126. Those are millimeters. And this should give us this final length of our specimen. Okay, here goes. I'm going to do that now. Oh, wait a minute. Then you'll have to add it to the original 50 meters. You can either do it that way or you can put a 1 in here. Let's do it that way. I'll put a 1 in here. And this is going to give us our final length, and here goes. I'm going to do that now. I'm getting 50.75, 663 millimeters. See, it started off with 50 millimeters. It increased to 50.87. They took the load off, and now it's 50.75. Now, what did they want us to find? They wanted the permanent elongation of the specimen. Well, see, the permanent elongation is that 0.75. It was originally 50, and now it's 50.75. So the answer in the back, see, that's a deformation. That's a little symbol delta. The answer in the back should be, if we did everything correct, 0.7563 millimeters. That's called the elongation. Another name for it is the deformation. It's the permanent deformation. Now let's look it up. This was a fundamental problem F311. We have 5 minutes left. We might have more fun. Help me find fundamental problem 311 here, and we'll see what they said. 311. They said 0.755. Now, what did we say? The book says 0.755 millimeters if you go to the back, F311. And F311, yeah. Well, we're pretty dang close. I wonder why we're off a tiny bit, but I am not going to obsess about it. They got 0.755, we got 0.756. And I hope you understood it. All right, now we have 4 minutes. I want to show you this modulus of resilience now. We got time. Are you happy with that? Any last comments or words on that? Okay, and you know you have that test. I forget when it's due. I think it's tomorrow night, maybe? Is that what it was?
Hey, Mr. Griffin.
Yeah.
I uploaded the test already, but I realized I made a mistake and I only uploaded the first page by accident.
Yeah.
So it's probably only going to be the first page of the grade. Can I just email you the whole test that I did directly?
Well, I'm afraid you're going to have to. Who am I talking to?
Brendan Harvey.
It'd sure be nice if you could have sent me the whole thing on Blackboard, Brendan.
Yeah, as soon as I hit submit, I realized that I only had uploaded the first page. I don't know why I did that.
Well, we're both learning. Hey, I'm learning this stuff too, you know. And let me
Yeah.
tell you, Brendan, it's harder for me than it is for you.
Oh yeah, I bet.
But yeah,
right.
we're not going to fuss with you. Okay,
All
now
right.
I got a little time. If you guys are all happy on this, we got time to show you the modulus of resilience, but I need the room. So I'm going to say goodbye to all that. That was fun. Wasn't that fun? Nobody said, uh-huh. Okay, now what we're going to do is find the modulus of resilience, and the symbol is u sub r, and all it is the area under the elastic region. Okay, it's the area under the elastic. Where are you going? Oh yeah.
Okay, bye.
I'll see you later. Okay, well, it's a triangle. Oh, gee, we only have 2 minutes left. I'm gonna have to hurry. But see this triangle right here? It's 1/2 the base, and the base is 0.00225 nothings times the height, which is 450 megapascal. Okay, I'm gonna do that now. And we'll get the, they have a name for it. It's called the modulus of resilience. All right. So you take 1/2 times 0.00225 times 450. Watch it. That's e to the 6th equals. And here's what I'm getting. I'm getting 50.6250. And you know what that is? That's pascals. In other words, it's Newton per square meter. That's what a pascal is. Now to get energy per volume, you just multiply by m over m. And see, Newton times meters is joules. Why don't we make this fancy? Why don't we call it 506.25 kilojoules per cubic meter? Did you understand that? That is the modulus of resilience. Now, if I had time, I would do the modulus of toughness. I don't, but I can tell you roughly how to do it. Roughly, remember the modulus of toughness is this entire area under the graph. Somehow you've got to figure out this entire area under the graph. Well, that's not that hard. There's a triangle here and there's a triangle there. You guys know how to do triangles, and this is a rectangle. So figure the area of that triangle and that triangle and that rectangle, add them up. And then you'll still have to do this little trick here in order to get energy in joules. If I had time, I would do that, but I don't. Okay, wasn't that fun? We're going to have to quit, though. Time's up. I will see you, I guess what, Tuesday at 9:30? That sounds good. Okay,
Yes,
bye-bye, students.
Goodbye. Thank you very much.
Bye-bye. Thank you so much.